Okay, then welcome to the lecture. Let's start, even though we are very few people. So we are discussing the notion of the tensor product of modules. That's a very important notion in commutative algebra. So let me recall, what is this object? Sorry, it was too fast. So I have, as usually, my ring A, and I have two modules, M and N. These are A modules. Okay, and we kind of construct a universal bilinear map. So what we construct an A module, which is called the tensor product. It's usually it's written this way. Sometimes people write here an A, but most of the time I will not do it. This is the tensor product of M and N, and this map always comes, okay, with a bilinear map, which is also called tensor product. So here I have a map, x comma y goes to something which is also denoted with this product symbol. So this is a bilinear. It's a bilinear map, and it's universal in the following property. So if you understand this in a way, you understand all, and more precisely, this means the following. So let's take P is any, okay, P, this is any A module. So note, I don't assume anything like finitely generated. It's completely general construction. And this module comes with a bilinear map, A bilinear. Then the statement is there is a unique factorization. So there is a uniquely defined map. It goes here. Okay, uniquely defined, which makes the diagram commutative. Okay, uniquely defined. Okay, A linear, uniquely defined. Okay, so this is the, I hope you remember. So the problem, this is quite abstract. So we will have some examples, then it will become clearer what this thing is, but right. So this tensor product has many applications, many applications, which is due to its generality and abstractness. Okay. So what do we do with this? I said, okay, most of the time. So I did the existence and uniqueness. Okay, we proved. Okay, we proved existence and uniqueness. Okay, uniqueness has a special meaning. You have to define what this means. You know, it means that, what does it mean? So let's say this is a tensor product, and this guy here is also a tensor product. Okay, why not? Okay, then the uniqueness statement is there is exactly one linear isomorphism here, which makes the diagram commutative. That's the meaning of the uniqueness. Okay, and we also proved that. Actually, this is by general nonsense. Whenever you have an object characterized by such universal property, it's automatically unique in this sense. This is always the case. Right. So from the construction, let me make a remark. And for proving the remark, I actually refer on the construction. That's very convenient. It's about the generators. So what are the elements of this M tensor N? Okay, and the remark tells me that every element of M tensor N is a finite linear combination of X tensor Y. Okay, any, I can write it this way, M tensor N is generated as A module by, okay, by this set of tensor products. So, okay. So this means what I said, okay? Every element of M tensor N is a finite A-linear combination of such things. Okay. So if, okay, so it follows from construction. So okay, you just have to remember, how did we construct this thing? What did we do? We took the free A module, which has as a basis M times N. Okay, and then we took a factor model, factoring out all the relations we needed. But the free module, I mean, what is the free module? With this basis, I denote it this way. Okay, okay, we had a factor model of this. But this free module has as a basis M times N. So it's generated by those. And this property obviously goes to the factor module. So it's, I think it's clear. Okay, so conclusion, which is very useful. So if I have two families of generators, let's see, I have here a family of generators and Y. Okay. Are families of generators of M and N respectively. Think of A modules. Then the products of these generators, Xi tensor Yj. Okay. So this family, if you want, this generates the tensor product. I think this is also obvious. Okay, so what to do now? Okay, there are the good examples and like the bad examples. And there are properties to prove. So let me maybe start right at the beginning with some bad example, showing you then one has to be a little bit cautious with this notion. Oh, no, that's not true. First comes the general property and then comes the bad example. Okay, so okay. So here, a general property. So actually my goal is to, actually what we can do, we can even construct a ring, the tensor ring or the tensor algebra, where the product is given by the tensor product. So it means that this tensor product has very nice properties. It's commutative, it's associative, it's distributive, blah, blah, blah. And like the first step in seeing this is, what is the neutral element? And this is the following proposition. For any A module, M, we have the canonical isomorphism. We have canonical isomorphism. So what I want to say is this. I form A tensor M. I view as an A module over itself. So this makes sense. A tensor M is an A module. What is it? And the statement is, this is canonical isomorphic to M. Okay, we have a canonical isomorphism, and this maps the element X to one tensor X. Let's call this U. So in a way, A tensor M is like M. So A is like the neutral element with respect to the tensor multiplication. So let's prove this. So this is all the proofs here, they follow the same scheme. I mean, how do I prove I have an isomorphism? I have to show there is this map, and I have to show there is a map in the reverse direction, and I have to show if I compose them in the two ways, I get an identity. Okay, the first thing is claim. Okay, or what do I do? Oh, first write it. I claim, I have a well-defined A-linear map from A tensor M to M with this property. sending the elements A tensor X to AX. Okay. So, I mean, for people that are familiar with the tensor product, this is all completely trivial, but as you are beginners, let's be careful. So how do we know that this map exists? Okay. You see, in linear algebra, over fields, if you define a linear map, what can you do? I mean, you write what it is. But the problem is that this A tensor X is not a typical element of my module. You see, I know every element of the module is a linear combination of those or a sum of those. This is true by the remark, but it's not unique. Okay, so how can I define it this way? It's not clear. You see, I don't have a base in linear algebra or fields. You can say, okay, I have a basis. I say, where do the basis elements go? But there is no basis. So what can we do? Well, the answer is the universal property. Okay, and it's always the same principle. So let me maybe here in the box explain. So what I for sure can do, I have this A bilinear map. Okay, A comma X goes to AX. So this map is A bilinear. Okay, this is a well-defined map. Okay, there's no problem with it. And it's bilinear by the axioms of the A modules. Okay. And then you use the universal property. Let's go down here. Here is this tensor product. It comes with this tensor map. Okay. So A comma X is mapped to A tensor X. And then I know by the universal property, there is this unique A linear map. Unique A linear map. I don't know, does it have a name? Yes, maybe B. Okay, so this is the B. Okay, so I have shown the existence of this map. Okay, so this argument you do 100 times without saying it anymore once you know how it goes. Okay, right. So by the way, this is an arrow. Sorry, this is maybe.
Yeah, sometimes the connection is making problems. Is it my problem or
I don't know.
the same for you?
I was wondering about that as well. No, I've also had issues with that.
My daughter, she is studying online as well, and she told me she has problems sometimes with the connection. Probably it's in our house. Sorry for that. Okay. Tell me if if there are things that you not understand because of this problem. Okay, so now let's see. Now I have the map U. The map U, of course, is well defined. There's no problem. So now let's, I say this is clear. Clear. When I do first U and then B, I get the identity on M. I think this is clear. X goes to one tensor X goes back to X. Okay. But now how the other way around? Okay, so now maybe I do it here. U tensor V. Okay, first V. Now I see what do I do on this generator A tensor X. Let's just calculate it. This is U of, and what is V of A tensor X is AX. Okay, and what is U of AX is one tensor, and now I put parentheses to be 100% clear. Okay, now I use that my tensor product is A bilinear. So I can pull out the A. Okay, and I can move it in to this side. Okay, I'm going very slowly. This is by bilinearity, and A times 1 is A. So what I have shown that, okay, U tensor V, U composition V behaves as the identity on the generators. Okay, but because these are generators, I get this. Since the A tensor X generate this. So this is the proof in very much detail. Okay. So there is a certain way of thinking, but otherwise it's in a way trivial once you know, right, what to do. Okay, so now let's move to this example. So there is a funny example here. Let's do this example. So what I do, I look, my ring is now the integers. So I look at modules over the integers. This is the same as looking as abelian groups. Okay, and then I have this submodule 2z in the integers. So the even integers form a subgroup of the integers, clearly. Okay. And there is another, okay, I have this other module, z modulo 2c, okay, as z module. Okay, now I want to know what happens if I take the tensor product of these two guys. So tensor, this. The tensor product is over the integers. I don't write it. What is it? Okay. All right. What is it? Okay. Sometimes one has to be careful. Sometimes these guys can be zero. But here it's not the case because look. Oh, maybe I should have said. Okay, maybe I moved down. Maybe we note the following. This is isomorphic to this. Okay. They're isomorphic. I mean, x goes to 2x, vice versa, right? So there is nothing strange about it. So, okay, so now, so I can say this actually is isomorphic to the integers times this. Well, now I use my proposition to see this is isomorphic to this. So this is the proposition. So my module M will be this guy. A tensor M is M. Okay, so this is isomorphic to that, right? Okay, it says my internet connection is unstable, but can you still hear what I'm saying? Okay, good. So, but now, what do we do? Now let's have a look at this funny. Right, you see, what do I do? Now I get this map. Okay. Okay, I claim I have here a map to the integers tensor this. This is a canonical map. When I say map, I mean morphism, of course. And what does it do? Okay, let's take an element here, like 2. 2 is a generator of 2z tensor. And okay, let's just put y. I mean, this, this object has just 2 elements, 0 and another element. Okay, maybe y, okay? That's just 2 elements. So, okay, but this should go to here. 2 tensor y. So, okay, I'm very careful here. So why is this map well defined? It's the same story as before, okay, by the universal property. Okay, defined, maybe put in yellow, defined by universal property. So again, you say, I mean, it's the same picture. Maybe I add maybe here. I mean, what you actually do, you have this. Okay, you do. Okay. Okay, and the map is this. This is bilinear. And then you factor via the tensor product. And you get this map. Linear, okay? Linear. This is this map. Okay? So you see, mathematics, there is some ambiguity. You see that I always write tensor, but you should be clear that this tensor is not the same as this tensor. Same here. This is not the same as here. Well, this depends on the context. We know that, okay? Multiplication can mean many things. And now comes the strange things. Sorry. Let's do a little calculation. I'm going to show that, right, okay. Okay, the claim is, first of all, first claim is this is non-zero. Why? Because this comes from 2 times y. I mean, under the canonical morphism. And this comes from y. Okay. And y, let's say, okay, I would say if y non-zero. Okay, I take y. Okay. Right. So sorry. So this thing just has 2 elements, 0 and y. Okay. So sometimes y is the special element, but it can also be general, right? You are not confused, hopefully. Maybe, okay, maybe let's put the y, what is a good name? Y bar. Okay. Y bar. Okay. So good. But, okay, now comes the strange thing. Now I look on the right-hand side. Okay, maybe one should use colors, but okay, I will not do it. On right-hand side. Okay, let's see. I'm gonna rewrite this. Okay, looks pretty trivial what I'm doing. 2 is 2 times 1. There is no doubt about this. Now I use the bilinearity. I pull out the 2. Okay, and I move it here. Okay. And 2 times y is 0. So it's 0. And 1 tensor y must be 0. So I worked here on the right-hand side. So this is here. So what I showed, that this is 0. Okay? You can't do anything about that. It's like that. Okay? So, and what we observed here, okay, maybe I can say it a little bit more generality. So the following can happen. So maybe let's put as a remark. So let's assume I have submodules m prime of m, n prime of n, be A submodules. Okay. So by the universal property, I have an A-linear map, have A-linear map such that, okay, what do we do? It's the usual, right? So maybe, okay, we go slowly. M prime times M prime. This is just inclusion or product of inclusion, if you want, to M times N. Here I have my tensor product map. Okay. Down here, I have another tensor product map. You see, this should have another color. Now this is going to be green. Okay. And then I get this canonical A-linear map, maybe phi. Okay. So the point is what I want to say, this phi is not necessarily injective. Okay. So warning, phi may not be injective. So in a way, this M, you see, what I would like to have, I mean, I would like to see this as a submodule of this, but it's not always possible. So the example, the reason is the example from before. Okay, example, take example from before with even with m prime equals n. Okay, it was this example. M prime 2z in the integers which are m. Okay. So maybe if we look at the tensor product over fields, if my ring A is a field, then this cannot happen. So then no problem, no problem. So this is only occurs when the ring A has torsion. Okay. Right. Questions on that? Okay. This takes a little bit of time to get used to, I think. So now let's continue with a little bit of abstract nonsense. Like mathematics is just what one has to do it, of course. So I have another remark, which is pretty obvious. It just says, I can also define the tensor product for more than two modules. Okay. Okay. Similarly, can define tensor product, okay, of many, finitely many of these guys. Let's say R many, okay, of several A modules. MI. It's the same thing. Instead of two, you have many. Instead of bilinear maps, you look at multilinear maps, okay? Okay, look at A multilinear maps. Okay, I think there's nothing, or is it clear? I mean, I don't want to bore you. So, okay, I mean, maybe I still do it. So, I mean, what I have is this. I have a tensor product map. This is multilinear. So it's linear in each component. And whenever somebody comes with an A module on the multilinear map, there is a unique way. Okay, it goes the other way around. A unique way to factor here by an A linear map. The same thing. Same existence, same uniqueness. No. Okay. But this is useful, of course, to have, because now I want to, in the next proposition, which is in Atiyah McDonald 214, it's about these properties that allow to construct a tensor algebra. Okay, even though I don't think I want to go, I don't really want to follow this in detail, but I write the properties. Let's assume I have M and P A modules. Okay, and then there are unique, okay, A linear isomorphisms. Okay, so now property one. On the one hand, M tensor N, I would like to say M tensor N equals N tensor M. Okay, but I cannot really say this. I mean, you see, you should even think of M tensor N is not defined absolutely. It's only defined up to canonical isomorphy, right? It's not. So the statement is there is exactly one isomorphism. such that, okay, x tensor y goes to y tensor x. But I write that below. Let me finish. I mean, this is associativity. And this is distributivity, I guess, right? So here, this is now direct sum. Here is tensor product. And I have a canonical guy here. So there are unique A-linear isomorphisms such that, let's call this ABC. So X tensor Y is mapped to Y tensor X under the first map. The second map should have this property. Okay, it's completely obvious what you want to have. This should go here. And see here, I mean, okay, instead of direct sum, maybe I write the pair. Okay, that's why he defined this external direct sum. X comma y tensor Z should map here. X unreadable, sorry. Okay. So this is this proposition. So up to canonical isomorphism, I have commutativity is here, commutativity, associativity, distributivity. So it means I get the calculus. Okay, I get a calculus which is very, as we know it from other places in algebra. Okay. So this proof, okay, is way boring, but okay, but let me explain a little bit. But not every step, it would be just too boring. But I say in principle how it goes. So the proof method, always the same. 2 steps. First, you show the existence. I mean, I have to come up with these maps. I show the existence of the A-linear maps via universal property. Show existence of A-linear maps by universal property. Okay, I think I used this already twice. And then, so we have to show the existence of maps in both directions, okay? And then we show these maps are inverse to each other. I'll show that. 2 maps are inverse to each other by verifying or by checking this on the generators. On generators. So that's the method. Always like that. Okay. So now you tell me if you, so okay, in my notes, I was planning to, what did I want to do? Distributivity, but you tell me if you want to see it. Okay, I would, if you want, I can explain to you the proof of this. Maybe this is the most complicated of the 3. But if you tell me you see how it goes, and so then I will not do it. You tell me.
Maybe just do it.
Okay, good. This is probably the good answer. Because once in your life one has to do it. Of course, it's not my first time. Good, let's do it. And you see how it goes. So proof of 3. Distributivity, okay? And the other is another. Okay, rest I leave as exercise. Now, so I consider the A-linear map. Okay, so I claim I have an A-linear map. Here I have, okay, this is the direct sum times P, Cartesian products 2. M tensor P, direct sum N tensor P. And this map, what does it do? X comma Y comma Z is sent to X tensor Z comma Y tensor Z. So and this is even wrong. It's not a linear map, it's a bilinear map. Sorry. Bilinear map. So you see, there is no problem. I mean, to define this map because every element on the left-hand side has this look. So I can write this map is well defined. And then I check, and this is trivial, that it is a bilinear. Okay, it follows from the properties of the tensor product. Okay, so I have a bilinear map. And then, okay, and then this gives me an alinear map by the universal property. It defines a unique alinear map. Okay, now what I have to do now, adjust these times. I replace, maybe this would be nice to have in color. Okay. And the right-hand side is unchanged. And what I want, of course, what do I want? X comma Y tensor Z, maybe in orange, should go to, I mean, what I have on the right-hand side. I just copy it. This has a name. Let's call it alpha. Now, this is the universal property. Okay, you see, it's the universal property. So this map is well-defined, alinear. Okay, now we go the other way around. Consider now a bilinear map. Okay, so here okay, what do I do? Right, we always have to think a little bit, okay? I have to go in steps. Okay, so I'm going very slowly. Right. So X comma Z goes to X comma 0 tensor Z. This is a bilinear. Okay, which induces the unique alinear map. Now here tensor product, direct sum, tensor product, and is characterized by the property that X tensor Z goes, that just copy. So I have this alinear. It's well defined. It's all about well definedness. Okay. Similarly, define a linear map. Okay, now instead of M, I want to have N here. Okay. Direct sum, tensor P. And Y tensor Z goes to, what will it be? 0, Y tensor Z. Okay, it's just I have exchanged the roles of M and N. Good. Okay, now this is called nothing. Now I combine those two maps. Okay, combining defines the A linear map. Okay, what will it be? M tensor P direct sum. Let's put maybe parentheses for the sake of clarity. Okay, and here same as before. So this I will call beta. and it will map X tensor Z. It's basically a writing exercise, this proof. And here on the right-hand side, I have to take the sum of these things. Okay, X comma 0 tensor Z. Direct sum, oder einfach sum 0 comma Y tensor Z. Maybe I should not, let's put the Z prime here, because here, yeah, otherwise it's not general. Okay, now I have maps in both directions. And I have to check they are inverse to each other. Okay. Okay, claim 1. This first alpha, then beta is the identity. I check on generators. Okay, it's always, where am I? The alpha goes from here to here. So I take, what would I do? I take X comma Y tensor Z. Then first alpha, then beta. Okay, now let's see. First, I have to do alpha. So what was alpha? Let's not check. Okay, this was alpha. Okay, this was alpha. So let's plug in this alpha. Then beta I copy. Then I have X tensor Z. So these proofs just must work. Okay, otherwise the world breaks down. It has to work. Then have this. So now on beta, now I look at the definition of beta is here. Okay, I should have simplified. Okay. In general, this I cannot simplify because Z may be different from Z prime, but if Z equals Z prime, I can use distributivity and simplify. So I get this plus. And I simplify this to X comma, okay. Okay, why not? So this distributivity, and this is the tensor product, this bilinear, and this is X comma Y. Good.
You're muted.
Recording is still working, I think. Yeah, sorry about that. So did you, yeah. So you see, I mean, by this calculation, I showed, in fact, okay, this, I mean, this is the same. Okay,
I think the screen share has stopped as well.
You're right. Everything has stopped. Right. Let's move down my list of participants also so I can see. Okay, so you see, orange is the same. First alpha, then beta is identity because these guys here, they generate. Okay, now the other way around. Okay, so this is the claim is okay. So claim 1 follows. Now claim 2. First beta, then alpha is the identity, check on generators. Okay, so these proofs on the way are completely automatic. It's like adding numbers. It just takes a little bit of concentration. It's equally boring in a way. Okay, but there are some concepts to have. One has to learn how to deal with them. Okay, so here, a little bit of concentration is needed. You just have to check where are my elements. So now I do it. I write and you check, because writing and thinking at the same time is not always so easy. Okay, now this was beta. Right, now I use alpha is a linear. Okay, now I should remember what was alpha. What was it? Let's go up. Ah, okay. Next that one. Okay, good. Okay, so this gives me x tensor z, comma 0 tensor z. Here analogous alpha, and here 0. Right. Okay, 0 tensor z prime y tensor. Okay, I'm going no very, very slowly, but of course 0 tensor something is 0. And the alpha has actually gone. Sorry, that was wrong. Alpha. And also the alpha here is gone. No alpha anymore. So, and then this is x comma z comma 0 plus 0 y comma z prime. And then what? Right. So if I did everything correct, this is the same as this, and this is good. So claim 2 showed. Okay, beta is inverse of alpha. So this proves property, it was property 3, 1 and 2 analogous. Okay, I consider this as proof. Okay, kind of general nonsense proof. I mean, it's just this method. Okay, so the difficulty is to understand what is the meaning of the statement. Once you understand it, then I think you can prove it. Questions on that or? Okay. You know, sometimes I really wonder, you know, I'm not only algebraist or some people, I do also other things. So it's like I also can take distance from algebra. Okay, I can pretend I'm working, I don't know, in another area. I look at algebra and it's really surprising how effective is algebra. I mean, you have a calculus, and sometimes it even, if you look at it in a macroscopic way, it looks trivial. But still you can do so many things with it. So this is a bit surprising. Okay, this is one example. Even though at the moment probably it's not convincing why is this good, what we are doing. Okay, so this extends. Let me also proposition 214, part 3, which I just proved extends to easily. So this is for you. Okay, instead of a direct sum of 2, I have a direct sum of, you know, any number can be infinite. I have this, sorry, it's not, yes, it's direct sum, tensor n. I have a canonical isomorphism here. Maybe I wanted to write easily extends. Okay, easily. Basically same proof. I mean, just you need a bit more letters to write it. For any family, mi of A modules. So we see direct sum commutes with tensor product in that sense. Okay, so now let's state something that really allows to understand what is the tensor product in certain important situations. Namely, the point is this. If, right, I showed you this example, which was a little bit pathological, but if one of the two modules, I could take the tensor product of two modules. If one of them is free, then it's much simpler to understand what's going on. And if both are free, the tensor product is also a free module and it's easy